Hi, my name is Manish Gupta, and in this video, I'm going to talk about AudioGen, which is an LLM for audio generation. Okay, so what is AudioGen? And rather than me actually talking about in detail about what is AudioGen, which I will do, in the later part of the video, let's see some examples to understand what is AudioGen and what can it do. It's basically auto-regressive generative model which can take text captions as input and generate audio, which corresponds to those text captions. Let's look at several examples in this small little clip. Notice the caption at the top and the audio on the bottom. So AudioGen is this nice large language model from MetaAI, which is basically auto-regressive generative model. As you saw, it can actually generate really high quality audio samples conditioned on descriptive text captions, right? Uh, it can also generate conditional and unconditional audio continuation. So by this, what I mean is that if you give some initial sound, let's say for 1 second, can it complete it for the next 4 seconds? It can actually do that, especially if in a conditional or unconditional manner. So you can actually give 1 second audio and then tell it using some text that, hey, continue this audio, keeping certain things in mind. It can actually do that as well. Okay. Now, if you think of it, this problem is really, really complex because of these following reasons. So how do you differentiate objects? That's complex, separating, multiple people simultaneously speaking in the same audio, or man is speaking while typing on the keyboard. So keyboard sound, man sound, right? So several different objects may actually participating in the audio, and it's difficult to differentiate them. Real world recording conditions also play a role. For example, there could be background noise in these audios which are used to train this model. Scarce text annotations. So typically for other kinds of data like image to text or video to text, there is lots of labeled data, but audio to text, there is not much of labeled data, right? Audio caption is not really a very popular area in that sense. Also, modeling high fidelity audio sort of requires encoding the audio at extremely high sampling rates, which basically means that you have long sequences. And long sequences are in general difficult to handle with transformer-based models. All of these basically cause little complexity in terms of doing this text to audio generation. In fact, consider this particular example. Let's say if we ask the model to generate an audio corresponding to this caption. A dog barks while somebody plays the trumpet in a busy street. Okay, so dog is barking, somebody is playing the trumpet, and it's a busy street. Model must actually generate three different categories of acoustic content, right? Something that denotes busy street, something that denotes trumpet, something denotes the dog barking, and with different degrees of background and foreground, different durations, different relative position in the temporal axis, right? So all of those are interesting things to take care of when doing text to audio generation. Okay. So how is this AudioGen model trained and how does architecture look like? So well, the architecture looks like this. Okay, so this is stage 1 of training and this is stage 2. So the stage 1 on the right side that you see is basically training an audio model. So in the sense, something that can actually take an audio sequence and come up with the audio discrete units as they are mentioned here, right? Um, and then the stage 2 basically makes use of this audio encoder, so to say, and essentially puts it right there. Okay. Along with that audio encoder, it basically also combines the text caption that is there and then finally generates an audio at the output that you just heard on the previous slide. Okay. So the training is done basically in 2 stages. The first stage is basically, as I mentioned here on the right side, it encodes raw audio to a discrete sequence of tokens using this neural audio compression model in that sense. So this is a bottleneck layer, and this is basically the encoded discrete sequence of tokens. As you can see, it basically makes use of a convolutional autoencoder architecture. Here are several convolutional blocks that you see here. More details are there in the paper, of course. The more interesting part is that, of course, it's an autoencoder architecture, which basically means input is an audio, output, it basically tries to reconstruct the audio. However, the way it is trained is basically using GAN-based objective functions. So there are, of course, there is a generator and there is a discriminator. The discriminator's job is essentially to minimize perceptual loss. And in fact, they use discriminators at different frequency and time scales, and therefore, there are multiple discriminators rather than just one discriminator. Now, the generator actually has also multiple loss functions. Of course, there is the traditional adversarial loss for the generator, which has to be minimized. That's basically there. I mean, it's sort of generator and in a GAN-based framework, generator and discriminator are always playing the game in that sense, right? So that's a traditional adversarial loss. But then there are other loss functions also that the generator tries to optimize for. So it tries to minimize the L1 distance between the target and the reconstructed audio over the time domain. So whatever audio you get, over the time domain, it must reconstruct as good fidelity as possible. For the frequency domain, it should also reconstruct the audio which matches in the frequency domain. So they use L1 and L2 losses over the MEL spectrogram using several time scales. So that's basically about the matching the fidelity and the frequency domain as well. Lastly, they also have a feature matching loss between the actual and generated sample in terms of discriminator probabilities. So you have discriminators and at different scales. So what you want is that if you have the actual audio and the reconstructed audio, both of them, the feature, the features or the probability prediction probabilities from those discriminators, the distribution should match as much as possible. Yeah. So for the generator, effectively, they have these 4 different loss functions, while for the discriminator, they basically have these typical perceptual loss minimization kind of a loss function. Overall, they effectively do a very good job at training this encoder model, which takes an audio signal and then gives you these discrete audio units. Now, in the second stage, they basically take this encoder well, given audio, it comes up with several discrete units. They also take the text caption. They use text encoder. In this particular case, they just use T5 model here, right? And then they give these two things along with the positional information as input to k different self-attention and cross-attention kind of layers. Now, so that's that. So this self-attention and feed forward happening around here, and this is basically a GPT-2 transformer decoder. The decoder, of course, does its job and decodes the audio outputs. In fact, it decodes the audio tokens, which are basically then passed to the decoder. So this decoder is actually the same decoder as you see there. Okay, so it basically generates the expected audio. Okay. So at inference time, how do you make this work, right? So at inference time, what's going to happen is that, you sample from the language model to generate a new set of audio tokens given the text features. So you have the language model, you basically take that, sample from that. Let's say somebody said, hey, I want an audio of a particular kind. So you pass that caption as input here. And then essentially you start generating these audio tokens one by one from the transformer decoder. You of course have the audio decoder, which basically takes those audio tokens that are generated and actually creates the waveform, the audio waveform. Yeah. Now, while training this architecture in stage 2, you randomly omit the text conditioning 10% of the for 10% of the training samples, and you do that because you want to do audio generation both in a text conditional and text unconditional manner. And therefore, in some ways, you sort of try to do classifier-free guidance in that senses by removing this text conditioning information 10% of the times. Now, to train the model, you need, of course, label data. So audio along with some sort of text captions. Now, there are 2 kinds of data sets that they exploit. In fact, they deal with lots of interesting data sets, right? But overall, there are 2 kinds of data sets. Some data sets have tags as labels. Some, of course, everything has audios, of course, audio clips. But then some have tags as labels. Some have a full, full nicely written captions as labels. So for example, if there are labels like dog and brown and running, you can actually create a short caption from it, brown dog running, something like that. So some data sets have just tags and they combine them to form a reasonable caption out of it, while some other data sets actually have captions with them. So as you see, these data sets, some of them are very, very small, while just this audio set data set is pretty good, 5.42 or other 5,420 hours, right? So overall, after cleanup and so on, they basically end up with about 4,000 hours of audio data combined with text captions, which they use to pre-train this AudioGen model. So how does this AudioGen model perform? Well, to evaluate performance, they basically use these metrics. The FAD metric, Freshet audio distance score. This is basically derived from an equivalent Freshet image distance score, right? So the definition is pretty similar. They also measure KL divergence between the actual waveform and the waveform which is generated. And then they also have two human measures, overall quality and relevance to text input. So this is, of course, measured by human labels, these two, overall quality and relevance to text input. Okay. So this is basically the result for audio generation given text captions, right? So as you see here, they have trained two different sizes of models, AudioGen base and AudioGen large. Right? AudioGen base is 285 million parameters. AudioGen large is 1 billion parameters. Now, while using the data, 4,000 hours is probably not enough. So therefore, they also do data augmentation by doing a very fancy scheme. So they take some audio samples and mix them while they concatenate the text captions. That basically creates a new sample and so on. So they do some augmentation. And then for the text conditioning, essentially for the final generation, they essentially have, so for the text conditioning, the text encoder, they essentially use T5 base for AudioGen base and T5 large for AudioGen large. Okay. They compare with an existing baseline method called diffsound, which basically makes use of clip as a text encoder, and it is 400 million parameter in size. What you observe is that across all these metrics, and of course, overall quality, higher the better, relevance to the text input, higher the better, Freshet audio distance or KL divergence, lower the better, right? So what they observe is that AudioGen base in general is actually better compared to diffsound. So if you look at these two, you observe that AudioGen base is better than diffsound. They also observe that, of course, the AudioGen large is much better than diffsound or AudioGen base. And in general, mixing, putting up these augmentations in general gives you better results. Okay. Now, the second set of experiments that you see here is related to giving audio prompts as input and asking the model to complete, right? So now the experiment with several settings that you see here. So for example, the audio prompt that you provide could vary in length. So there could be 0.5 seconds, 1 second, 2 seconds. So this is what varies on the x-axis in these charts, right? Up to 4 seconds. You could also have different combinations of text prompts. So for example, you may not give any text prompt whatsoever. So no text prompt. There's a small audio, maybe 1 second audio. You want to fill in the next 4 seconds, something like that. Okay. Or you could basically give the text corresponding to that particular audio only, right? So that helps in that senses. Or you could give some random text, and basically, although the current audio corresponded to some text, but then you give some random text, thereby asking the model to continue from whatever audio was played, but then it should basically modify the audio corresponding to the text that was given to it. Okay. So these experiments actually show results around that. So let's look at the first one. So this one is basically on x-axis, you see the audio prompt duration. On the y-axis, you see KL divergence. So lower the better. So on the y-axis, always lower the better. Okay. And you actually see two curves here, random text and source text. So what you observe is that if you give source text, in the sense, you played, for example, 0.5 audio prompt, but then you gave the entire source text, you actually observe that as the prompt size increases, the source text helps and helps to come up with a better audio because the KL divergence is reducing. However, if you look at random text in the sense that you have given some audio prompt, but then you've given some other text and you have actually asked the model to modify to have a good continuation with the current audio, but then modify the audio so as to suit the random text. Well, it becomes more and more difficult to do that if your audio prompt is large in size, because if already a lot of audio has been played, then it's very difficult to modify that so as to suit a new text altogether now. Okay, so that's one observation. The second chart basically is against audio corresponding to random text. So let's say there is a prompt and then you have some random text being played. a random text being given as conditional input. So if you give this random text as conditional input, as you observe, this curve is exactly the same as this curve. You sort of observe that it becomes difficult to generate reasonable audio using random text if your audio prompt is pretty good and pretty large in size by itself. Okay. Now, of course, if you do not pass any text for any help, then basically KL divergence is pretty high, which means the quality is not as good anyway. Okay. Now, this one is very interesting, where you essentially provide either you provide text or you don't provide text, but you provide the source text only. Okay. So of course, if you provide the source text, then as the prompt size increases, you observe that not just that there is enough information in the audio prompt already, but also this extra information that your text is passing in so as to generate a high quality completion. Right. So therefore, source text, whenever you pass on source text, it sort of helps you get a better quality completions. Now, if you do not have any source text, well, still the quality of the completion improves, of course, as the audio prompt size increases, right? So because if you have already a lot of audio in the prompt, then there's a good chance that you'll be able to complete it nicely. Okay, so in summary, in this video, I talked about AudioGen, which is basically auto-regressive audio generation large language model from MetaAI, which is conditioned on text descriptions or audio prompts. So it can basically take a small audio prompt and generate the full audio, or it can take a text caption and generate an audio corresponding to the text caption. There are two different sizes of AudioGen models, 285 million parameters and 1 billion parameters. Of course, the 1 billion parameter trained with augmentation gives very good results. Audio continuation conditioned on the text and unconditionally. So you can come up with continuations in conditioning on text or without any conditioning on text as well. And as we saw in the first part of the video, AudioGen actually creates more natural sounding unseen audio compositions, right? So it can actually really come up with the high fidelity audio. Okay, hope you like this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.